Good morning, everyone. We are ready to go. I've hit the record button. So today is one of my favorite classes or days in this class. There's a couple of them, but this one is one of my favorites because it's the first time early on in the course, fairly early on in the course, where we get to enjoy sort of the fruits of our labor. We've developed a theory of permutations, an ability to write them in a good way using notation that actually tells us some information about the permutation. That's our cycle form. We're able to do quick factorizations into 2 cycles, into 3 cycles. We now got this notion of parity, which tells us every permutation comes in one of 2 flavors. It's either an odd permutation or it's an even permutation. We got these additional results that say if it's an even permutation, you can always write it as a product of 3 cycles. So 3 cycles can produce all even permutations. And if you want to produce an odd permutation, you can write it as a product of an odd number of 2 cycles, or you could write it as a product of a bunch of 3 cycles and then 1 extra 2 cycle to make it odd. So we got all of these sort of results that are floating around. And today we bring them all together and use them to analyze the 15 puzzle. The first thing we did when talking about the 15 puzzle, we started this last day, was talked about a solvability criteria. So what a solvability criteria is, it's the ability to look at the puzzle in its current configuration and decide whether it's even worth your time to play around with it and try to solve it. Because it tells us that yes, it is solvable, or no, it is not solvable. And so that's what a solvability criteria says. It says, given the current state of the puzzle, you're able to determine whether it is possible to solve it or it's impossible. Solvability criteria are things that we're going to be developing for all the puzzles. This is where the theory really comes in. So even for the Rubik's Cube, we'll be able to look at a Rubik's Cube when it's all scrambled up and be able to say, yep, that's solvable, or no, that's not solvable. And it's not solvable because of these reasons, and here's how you would fix it in order to make it solvable. And we're doing the same thing for the 15 puzzle. So our first solvability criteria involved the 15 puzzle configuration where the empty tile was in the last spot, in the spot 16. And so as long as the empty tile is back where it's supposed to be, and all the other numbers are all messed up, we know that it's solvable precisely when the permutation is even. Okay, so I'd say we know that because that's theorem 9.1.1. We still haven't proven this yet, and that's what we're going to do today. But the idea here is that as long as the empty tile is in box 16, then it's solvable if it's even. If it's an even permutation, it's solvable. And so we did that check on these examples. We checked the first example, yep, it was an even permutation by just writing down its cycle form and counting up how many 2 cycles we need. We get that it's even, therefore solvable. The second one, part B, we got that it was an odd permutation, therefore it wasn't solvable. The best we could do in that case was get it down to a state where 14 and 15 were switched in position. If we were to solve them numerically, put 1 in the 1 spot, 2 in the 2 spot, and continue going that way, we would ultimately get up to 14 and 15 having been swapped and therefore not solvable. So that's the best we could do. The other way you could view this, though, is that if you look at this puzzle in part B, and you get that, okay, it's an odd permutation, therefore it's not solvable. That just means you put the tiles back in. When you randomly put the tiles back in, you threw them back into their positions, and now you're ready to go and solve, and you think to yourself, well, maybe I'll check to see if it's solvable first of all, and you get that it's not. That's no problem because you just pry out any 2 tiles, doesn't matter which ones they are, and you swap their positions. So pick any 2 tiles, 6 and 11, for example, just pick them up, swap their positions, throw them back in, and now it's solvable because it's going to be an even permutation. You added an extra 2 cycle to the mixed. So that's what we could do for the 15 puzzle. We can detect whether it's solvable or not, and if it's not solvable, we have a fix for it. Just swap any 2 pieces. In the last example, we had that the position was a 3 cycle, it was even, and therefore it was solvable, and I demonstrated a way we could actually solve it. So the 3 cycle was the 1, the 2, and the 5 tiles had been 3 cycled around. And so we demonstrated a way to solve that using a natural 3 cycle on the puzzle. That's what we're going to exploit going forward in today. Okay, so then we did a few counting things. I think it's important to sort of emphasize this next fact that everything we've done was based with the empty tile being back in the spot it started in. But what if you just randomly throw your pieces back in and your empty spot is not in box 16? Your empty spot is somewhere else. Can we still use the same ideas of detecting solvability using parity? And the answer is yes. We just have to be slightly careful in what we do. So let's look at this example. I skipped over this example at the end of last day to get to the main results, which we talked about already. But I think it's important to go back and sort of revisit this example again, because it does form the basis of the second solvability criteria when the empty space is not in the box 16. So we write down its position. So 1 is in box 1, 2 is in box 2, 3 is in box 3, 4 is in box 4, 5, 6, 7, 8 are all in their appropriate boxes. 9 is in box 9, so it's 10 is the first one that's been moved. It's in box 11, 11 is in box 12, 12 is in box 16, 16 is in box 10, and 13, 14, 15 are all solved. So what we get is this, and that's an odd permutation. Okay, so our general solvability criteria, or maybe I should say general, our specific solvability criteria when the empty tile is in box 16 would say you just need to know if it's an even permutation or not. But here the empty tile is not in box 16, and we have that the position is odd. So we can't conclude at this point whether the permutation or the arrangement is solvable or not, because it all depends on where the empty tile is. And if you look at this configuration, you can see that all we have to do is slide 10 over, slide 11 over, slide 12 up, and we've solved the puzzle. So this one is solvable. Even though our permutation is odd, it is solvable. So this is solvable. But the position is odd. Okay, so that means the empty tile really has something to do with this as well. So let's look at our empty tile or empty space. Where is it? It's in box 10, which is 1, 2, 3 moves away, 3 moves from its home position. What's its home position? Its home position is box 16. And 3 is odd. So that's the thing here, is that this is odd. The empty tile is an odd number of moves away from its home position. The permutation itself is odd. And the fact that both of these are odd means that when you start with that permutation and you do the 3 moves to get the tile back to its home position, the configuration you're now staring at is even and therefore solvable. And so that's the key observation here. When the empty tile is not in box 16, figure out how many moves does it take to get there. And the parity of the number of moves it takes to get there has to match the parity of your current configuration. If they have the same parity, then it's solvable. If they have different parity, then it's not solvable. And notice parity in this case is parity of the permutation position, and you're comparing that with the parity of the number of moves to move the empty tile into box 16. So kind of parity of 2 different types of objects. One is a permutation of a position. The other is the parity of the number of moves it takes to get the empty tile into the home spot. So because we're interested in the parity of where the box the empty tile is in, the best way to figure out what parity is to just do a checkerboard coloring, and the shaded ones are even and the white ones or the non-shaded ones are odd. And that's because those are precisely the boxes that it takes either an odd if it's a shaded one, an even number if it's shaded, it's an even number of moves to box 16. And if it's in an unshaded box, it's an odd number of moves to get to box 16. And that gives us our solvability criteria in general. So this is part 2, but this is the general form of the solvability criteria that says the puzzle is solvable if the parity of the permutation is the same as the parity of the location of the empty space. So let's go ahead and apply this now. We're going to determine the solvability of these configurations. So the first thing we do is we write down our position as a permutation. 1 went to 7, 7 went to 9, 9 went to 1, 2 went to 4, 4 went to 11, 11 to 16, 16, which is the empty tile, it's in box 3, 3 went to 5, 5 went to 2. Oh, 2 is already, 2 is where we started, so I don't add that on the end. I close it off because it wrapped around now. So we've dealt with numbers 1, 2, 3, 4, 5. 6 hasn't been dealt with, but it's in its home location. 7's been dealt with. 8 hasn't been dealt with, but it's at home. 9's been dealt with. 10 hasn't been dealt with, and it's moved. So 10 went to 14. 14 went to 13. 13 went to 10. So that closes it off. So that deals with 10. 11's been dealt with. 12's in its home position, 13's been dealt with, 14's been dealt with, 15's in its home position, and 16's been dealt with. So we've got all the numbers dealt with now, and so there's our position. Let's figure out odd or even. 1, 2, 3, 4, 5, 6, 7, 8, 9. So the permutation is odd. And now we look at the empty tile, or the empty space. I usually refer to it as the empty tile. Where's the empty tile? That's in box 3. 3 is shaded, meaning that it's an even number of moves away from box 16. So it's in box 60, in box 3, the empty tile is in box 3, which is an even parity box. Okay, so one common mistake people make here is when they're looking at the parity of the box that the empty tile is in, they somehow try to look at the box number as if that's going to tell them. 3 is not going to tell you the parity. The number 3 in that box is not telling you the parity of the box. Number 3 is just our labeling for home positions, etc. What's the parity of the box is how many moves it is to get to the bottom right-hand corner. And it's an even number of moves. It takes 4 jumps to get there. Box 3 to 4, 4 to 8, 8 to 12, and then 12 to 16. So the thing is we look at these two parities and we say they're different, not solvable. So therefore, little triangle of dots, not solvable. Best case, we can get it into the form where 14 and 15 are swapped. Let's look at the next example. Position. 1, 2, 3, 4, 5, 6, 7, 8 are all in their correct spots. 9 has gone to 11, 11 has gone to 14, 14 has gone to 9. That takes care of 9. 10 hasn't been dealt with yet, so 10 went to 15, 15 to 16, 16 to 12, and 12 to 10. So that takes care of 9, 10, 11, 12, 13 is in its home spot, 14, 15, 16 are all there. So that's our position. Odd or even, 1, 2, 3, 4, 5. It's odd. I want that in green. It's odd. Empty tile. It's currently in box 12, which is 1 move away from box 16. So it's in an odd parity box. And since the permutation is odd and the empty tile is in an odd parity box, then it is solvable. So there we go. That's our theory of permutation so far that allows us to tell whether a puzzle is solvable or not solvable. So you may wonder, why or how this is possibly used. I mean, I'll just give you one example. If I bring over our 15 puzzle slide and this applet that was written by Yop, it allows you to edit it. So if you want to edit, I'll click edit here. Let me see if I blow it up. It's kind of small. Actually, rather than blow this one up, I'll just open the applet in a new window, which is already larger. I will go edit, and then I'll just start randomly arranging the tiles. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13. Watch, as soon as I click the 13th tile, the remaining 2 tiles, they are forced to be in a particular order. Because as soon as I click this one, there, I put 13. Oh, sorry, they're forced if I tell it which one is the tile that I want to be. I have to tell it which one is the empty space. Sorry, I was thinking about this one being the empty space. But as soon as I click the next one where the 14 is, then the 15 is going to have to appear in one of the other 2 spaces so that the resulting permutation is even. So if I click that I want 14 here, then it automatically, it made it so that the 14 and the 15 and the empty tile appeared here. That's fine. I forgot that it forces the empty tile down here. So I can do it again. 1, 2, 3, 4. It forces the empty tile into a spot. There we go. That's what I wanted. As soon as I clicked here, I was clicking where I wanted the empty tile to be, and so it forcefully put the 14 and the 15 in the appropriate spot. It couldn't have 14 down here and 15 up here because that would have been a permutation that was unsolvable. So that's the kind of thing that gets used in making these kinds of applications where you're giving the user the ability to, I'm trying to get this out of the way, where you're giving the user the ability to set the tiles up, and you want to make sure that it's solvable for them. So they really don't have a choice for that last pair of tiles. It's forced upon you based on parity. So that's one possible place that this kind of idea is used. So that allows us to detect solvability. The next thing I want to do is I want to prove the results. Now, I'm not going to go through the whole proof because I'm going to do kind of what I did in another case. The case of showing the parity theorem is I want to do an example or a number of examples which show you how the proof is actually structured. Examples are never enough to do a general proof, but examples are enough to get a feel for what you have to do in general. So that's why I've included the full proof here. And it looks a little bit overwhelming, and I don't want to go through it line by line, but I want to give you a feel for what the steps are and why they're necessary. So the first thing I want to do is I want to show theorem 9.1.1, that only the solvable configurations, or maybe I should say it that way, only the even configurations are solvable. If it's solvable, it must be an even permutation, and if it's an even permutation, then it's solvable. So that's theorem 9.1.1. That was where the empty tile was in box 16. One direction is fairly straightforward, as in some sense what we call trivial, and that is if it's solvable, then the permutation has to be even. So if the permutation is solvable, then it has to be even. And why is that? Well, I've got a bit of a description there as to why this is the case, but I'll demo it in just a second. The idea, though, is that if it's solvable and the empty tile's in box 16, then in order to solve it, you're just going to be moving the empty tile around the board, ultimately getting back to box 16. And so if you move the empty tile around the board and ultimately get back to box 16, how many moves would you have had to make? Well, let's scroll back up to our checkerboard diagram. I've got my empty tile here right now. And then what I have to do is I have to move it around the board to get my sequence of moves that solves the puzzle, and then bring it back there. Well, every time I do a move, I change the color of the box that my empty tile is in. So that's an odd number of moves. Now I've made an even number, odd number, even number, odd, even, odd, even, odd, even, odd, even, odd, even, odd, even. And you notice that every time I move the tile, I just change the parity of the box that I'm in. If I'm eventually getting back to where I started, odd, even, then I would have had to make an even number of moves. Because I start on a green tile, I end on a green tile, or I start in a green box and I end in a green box. So that's the observation that says that if the puzzle is solvable and the empty tile is in box 16, then doing the process of actually solving it, moving the empty tile around, you're going to have to bring it back to box 16, and so an even number of moves would have happened. And each move is a swap, right? Each move is a switch the contents of box, the first move was contents of box 12 and 16. So that's a 12-16 swap. And then I did a 12-8 swap. And then I did an 8-7 swap, and then a 7-11 swap. So each move is a swap. I do an even number of swaps to solve the puzzle. That means the permutation had to be even. So that's the first observation, is that if alpha is solvable, then the permutation is even. The second one is to do the other direction now. Suppose the permutation is even. Then we want to show it's solvable. That's the harder one to do, because what we're trying to show is that no matter what the permutation is, let's scroll back, we know how many of these there are. No matter what the permutation is of these 653 billion permutations, I want to show that they are all solvable. Now that's quite a feat we have to do, because it means we can't specifically focus on any one permutation. We need to show all the even ones are solvable. So I have to show all 653 billion of them are solvable, which means I have to come up with an argument that works in general. Now, when coming up with a general argument, we need something to hold on to. We need like an anchor. We need some fact that we can exploit. Reduce the what seems to be chaos, all 653 billion of these things, and we got to pull from them some property that we can exploit and use in our argument. And the property that we're going to exploit is this one here. Every even permutation is a product of 3 cycles. So of those 653 billion, they all have the same property. They all are expressible as products of 3 cycles. So that means if I can show that I can produce any 3 cycle whatsoever, then I can produce any product of any 3 cycles whatsoever, and therefore I can produce any even permutation. So we've taken these 653 billion and we've reduced it down to just showing that we can produce 3 cycles. And there's a lot fewer 3 cycles to produce. So we could go through and say, okay, now I'm going to show how to do a 1, 2, 3 3 cycle, a 1, 2, 4 3 cycle, a 1, 2, 5 3 cycle, a 1, 2, 6 3 cycle, and come up with every possible combination of 3 cycles and go through them and show that they're all possible. That's still a lot. So we're going to try to refine it even further. So we want to show that every 3 cycle is possible. Let's just try to find out if we can do some particular 3 cycles. And that's the rest of the proof is trying to show a particular set of 3 cycles that's going to be useful, but I'm not going to go through the proof line by line. Instead, we're going to go right to the puzzle and play around with it. And we're going to try to keep track of the kinds of 3 cycles that we can do. So let's think. I've got them all in the solve state right now. So this is now easy to detect whether we've done a 3 cycle or not, because we can see which tiles have moved. The very first 3 cycle that I'm going to say we know how to do is 11, 12, 15. Boom. I've got a 3 cycle. And it's like, great, I know how to do 1 3 cycle. Of the however many I need to show I can do, I've now showed that I can do 1 3 cycle. And we can do, so that's an 11, 12, 15. I could also do 11, 15, 12 by just cycling around in the opposite direction. So actually I know 2 3 cycles, it and its inverse. Okay, that's wonderful. We know how to do 2 3 cycles. I'm just going to scroll the other one back up. That's this first little bit here. First note, we can do 11, 12, 15. There's the steps I just did. So here's the next line. Using this I've used a sigma here to represent this fundamental 3 cycle. I call this the fundamental 3 cycle because it's the 3 cycle that is so fundamental to this puzzle that we often forget about it, but it turns out to be instrumental in getting all the other ones, is that just cycling these 3 tiles around in the bottom right-hand corner turns out to be the key to understanding the whole puzzle. So using this fundamental 3 cycle, what I'm going to do is I'm going to produce any 3 cycle 11, 12, I. We already know how to do 11, 12, 15. Now I want to do 11, 12, 1, 11, 12, 2, 11, 12, 3, 11, 12, 4, any of those 3 cycles. So let's see how we can do that. Let's maybe try for an 11, 12, I sort of said it in this order. Why don't we do an 11, 12, 1? So I want 11 to go here, 12 to go up here, and 1 to come down here. So I'm going to cycle 11, 12, and 1. Let's see if we can do that. Because if we could do that, we're starting to make progress on getting any 3 cycle. So how are we going to do that? Well, I already know how to cycle 11, 12, and the tile that's sitting right here. So if I can bring that tile 1 down here, then I could cycle it. So what I'm going to do is I'm going to keep track of the moves that brings 1 down to that bottom corner. I want to bring 1 down to here. In order to do that, the first thing I'm going to do is I'm going to hide 11 and 12. So I'm going to hide 11 and 12. Just going to bring them over here and I'm going to hide them. So it doesn't look like they're really hidden, but the idea is I move the empty square or the empty space out into the middle of the board more. And so I'm effectively putting 11, 12 to the side, and I'm never going to let those things move again until I'm ready to use them. Now at this point, I say, well, I need to bring 1 down here. So what I'll do is I'll just run it counterclockwise around. So I'll go just run the tiles, shift them all counterclockwise around this big loop. I'm bringing them all around this loop. Keep going until 1 finally gets into the spot I want it in. Getting there. And one's in the spot I want it in, but I also want the empty space with it. So all I did was just like turned a big wheel and finally got it to the point where 1 was in the box where 15 was. So I hid 11 and 12. I shifted everything around this big cycle to bring 1 to where 15 is. Now I'm going to unhide 11 and 12. And at this point, I'm pretending I'm back at the original board that I started with the one exception, is that now tile 1 is in the spot where tile 15 was. Now I can do a 3 cycle. The 3 cycle I wanted to do was tile 11 goes to tile 12, where tile 12 is, tile 12 goes to where tile 1 is, and tile 1 goes to where tile 11 is. So now I do that fundamental 3 cycle. There's that fundamental 3 cycle. So I brought them all together and then 3 cycled them. And now I'm going to send them back to their respective places. But I'm going to do so in such a way that I just reverse the moves that brought them together. So I've got all this mix of tiles. I bring them all together. I 3 cycle them. And then I undo all the moves that I used to bring them together. So the moves I used to bring them together was I hid these 2 tiles, the tiles that were in 11 and 12. I hide them. And then I undo turning that big wheel to get the tile that's here back up to box 1. So I just send everything around the other way. Undo all the moves I did. And at this point, you're probably thinking, which tile do we need to get up there? It was tile 12. Tile 12 was the one that ended up replacing tile 1. So I'm just waiting until tile 12s get up into that top corner. There it is. And my empty space is back here again. That's where I wanted it at the start there, because that was after I hid the 2 tiles that were in box 11 and 12. So I've now pushed the tile that replaced 1 back to the 1 spot, and now I undo the hiding moves. And if you look, what ended up happening? 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12 have been moved. 13, 14, 15. So it's these 2 tiles and this one are the only ones that got affected in the end. And so I'm able to produce an 11 goes to box 12, item in box 12 goes to box 1, item in box 1 goes to box 11. So I've just produced an 11, 12, 1 3 cycle. So that comes back to that comment that's made up there. Using sigma, we can produce any 3 cycle of the form 11, 12, I. I've just done an 11, 12, 1. Okay, let's see if we can do the same thing with an 11, 12, and some other number. 11, 12. Okay, those are all in the right spot. So in the chat, someone give me another number. So we want 11, 12, and some other tile on the board, and we want to 3-cycle them. So we got a 5 here. Thank you. So we're going to do an 11, 12, 5. So these are the ones we're going to mix up. I'm going to see if I have. I did have a set of Post-it notes. I was going to rip a little bit off of one and tag. Can't seem to see them right now. And I was just going to tag those tiles. But I can't seem to find any Post-it notes. I don't know where they went. Okay, so 11, 12, and 5 are the ones we want to do. So what I'm going to do is I'm going to hide. Actually, and there's one other thing I'm going to do here. I'm just going to scroll up so I get a little bit of blank pages here. Add new page. Let me get a new page. Add page. I just want a blank page that I can hide above. There we go. So I'm going to just keep track of the moves because this is going to help in the next homework assignment as well, is to know how to write down the moves. So I'm going to hide 11 and 12. So hide 11, 12. To do that, I'm going to do what is effectively a 12-16 transposition. I switch the contents of box 12 and box 16. But for the 15 puzzle, sometimes it's more convenient just to say I slid the tile down. So I slid it down. And this bracket is just grouping bracket. It's not a cycle bracket or anything like that. It's just a grouping bracket. So I went down and right. So that's hide 11, 12. Maybe instead of brackets, because I don't want you to get confused with cycles here, is just we're making a word. Down, right is the 2 moves I just did. So that hid 11 and 12. And now I want to bring, I don't know how long this is going to be, but let's just make it fairly long. Bring tile 5 to box 15. So that's the next move I want to do. Tile 5 is the thing we want to get involved in the mix, so let's bring it down to 15. So maybe I'll bring it this way around. I'll cycle 5 counterclockwise. So in order to do that, what I'm going to do is I'm going to do an up. So slide the tile up, then right, right, down, down, down. And then there's a couple of lefts here, left, left. And then 3 ups, up, 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 up. And then a couple of rights, right, right. 3 downs, down, down, down. Couple of lefts, left, left. 3 more ups, up, up, up. Couple of rights, right, right. 3 downs, down, down, down. Couple of lefts, left, left. 3 more ups, up, up, up. Couple of rights, right, right. And we've got 5 in the right spot now. Then there's 3 downs, down, down, down. 2 lefts, left, left. And 2 ups to get the empty space above it. Up, up. Ooh, we just managed to squeak that in there. That is bring tile 5 all the way down. So that's great because I brought tile 5 all the way down to where I wanted it. Sorry, I'm just going to plug my pencil in because it was showing me a battery warning. Now at this point, I'm hiding the last few moves, of course, with my video. There we go, up, up. Now we've got everything into the right spot. So this was in some sense our setup. We wanted to set up in such a way that we're now able to do the 3 cycle we want. So we wanted 11, 12, and 5 to get cycled. So I still need to do the unhiding part to get to the fundamental 3 cycles. So I unhide. So what's my unhide part? I'm going to move those over because I kind of want them all in one line here. So hide. and then unhide 11, 12. And that was, I'll show you what that was again. That was left up. In other words, it was the inverse of the hiding moves. The hiding moves were down right. We need to do the inverse. So left up. And that takes us to the stage where we look like we're almost like the original puzzle. Empty spaces in box 16, 11 and 12 are in their own boxes, except now we've put 5 where tile 15 used to be in box 15. So the next thing is do the fundamental 3 cycle. The fundamental 3 cycle was the 11, 12, 15 3 cycle. So we do that one. That's a down, right, up, left. Down, right, up, left. In other words, that was the 11, 12, 15 3 cycle. That's what that one was. Let's scroll this up a bit so we can see. There we go. Okay, so we've done the 3 cycle. That's the thing we wanted to do. We've cycled those tiles. 5, 11, and 12 have now been cycled around. Now we just need to undo all of our setup. So if this was our setup, now we need to do the inverse of the setup. So we just read it backwards and do the opposite move. I'm going to have to scroll this up a little bit more. See if we can get it in here. That's the inverse of our setup. So I just read it backwards. I'm like, okay, the last move was an up, so I need to do the opposite, down. So I'm reading backwards from right to left and just doing the opposite of everything. Down, right, down, down, right, right, up, 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 and so on, all the way across. Yeah, so that's just read it across, and we can write them all down. So the key here is we could write these things down if we wanted to. For this, though, we already know what happened. We took 5 and we tried to push it around clockwise. Sorry, counterclockwise. We brought 5 and down here like this. So then we need to do the opposite and just run it back the other way to bring that tile 12 back up here. So we have to do the hide again. So I'll just write this down as hide. Then, so that's this little bit here, hide. And then we've got undo, bringing tile from box 5 to box 15, and then undo hide again. So that's the structure. I'm not going to write these things down, but that's the structure that we have. Fortunately, I can't sort of fit all of this in, but that's the thing I kind of want. So that's the thing. So we've hidden. Now we undo bringing the tile. So we're going to undo by sending it around the other way. It's now tile 12 that's going to land back into box 5. And I think we're good there. Tile 12 is now back where it is. See, a lot faster to do when you don't have to write these things down, but that's the key, is that the writing down was that we could do this. We could keep track of moves if we start doing complicated things, and then we could undo them by reading them backwards and doing the inverse. So now we've got these things. Tile 12 moved back and everything's in its spot. And then we're at that last part, the undo hide. Undo hide. And there we go. We've done 11, tiles 11, or the tile in box 11 has moved to box 12. The tile in box 12 has gone to box 5, and the tile in box 5 has gone to box 11. We've just done an 11, 12, 5 cycle. Does that make sense? Yeah, exactly. That's a good observation. Yeah, the first time I did this, it did look like a magic trick. It's like, well, how did you do that? Now my trick has been revealed. And if we think about what I've in some sense done, I've done a bunch of stuff that tried to get the board looking like the original board, except whatever tile. So I'll move these things around and get these off. It's a sticky one. There we go. So I tried to take my original board, knowing that I could do an 11, 12, 15 cycle, And I said, well, if I can do that, then whatever I bring down here to this box, I can use it in a cycle instead of tile 15. So what we've done is we've done a bunch of stuff that brought tile 5 down here. And all the other tiles, all of these other ones got messed up in the process. Well, many of them did, maybe not all of them, but they all got messed up in the process. So I did something to bring them all down here. That's this thing up here. Let's call it gamma. Whatever gamma was, a big collection of moves that brought tiles 11, 12, and 15. So I did a gamma, and I'll scroll this up here just to see. So we did a gamma, and for lack of a better term, I like to call this first one gamma inverse. You might say, well, why? Well, I'm going to do the inverse anyway, so I'm going to have to talk about it and its inverse, but I like to have it written like this. So we did some move sequence. Let's just call it gamma inverse. Then I did my fundamental 3 cycle. Boom, boom, boom. And one more, like that. So I did my fundamental 3 cycle. And then I undid my gamma. So that means I undid my gamma inverse. So I did a gamma inverse, then did my 3 cycle, and then I undo all of the pink stuff, which if I called the original one gamma inverse, then the undoing is just gamma, because they're inverses of each other. And so that means I took this tile and sent it back up here. 15 comes back to this spot, and everything else gets restored. And there's my 11, 12, 15 cycle that I was looking for. So this is our setup. Or sorry, that's our solution process, where this was our 11, 12, 15, the one we know how to do. And all the other stuff, the gamma inverse and the gamma, was just merely setting it up to exploit that fundamental 3 cycle. So I'm going to pause there for a second. Does this make sense? Does this make sense? Okay, so the idea is you want to cycle 11, 12 and some other thing, just bring it down to box 15, do the cycle, and then send everything home. So I call this setup, do your 3 cycle you know how to do, and then undo setup. And it turns out that this, well, it turns out to be quite an important thing to do on all puzzles. If you know how to do one move, that allows you to modify it to make it do the same kind of move on everything else as well. One of your assignment questions this week with the SAGE explorations has you explore products like this, and how a product like this and the thing sandwiched in the middle, how do they relate to one another? And you can maybe start to see a hint as to what is important here. The fundamental 3 cycle, the thing in the middle, was a 3 cycle. And then when I did this gamma inverse gamma sandwiched on each side of it, I still produced a 3 cycle. So the cycle structure doesn't seem to change. If I start with whatever cycle structure sigma is, then doing the sandwiching effect will keep the same cycle structure. It's just the numbers will change inside. What you're 3 cycling will be different. Or if sigma was a 4 cycle followed by a 2 cycle, then what you're 4 cycling and 2 cycling will be different numbers than what sigma originally did. And it depends on what the gamma does, what it brings into those spots to do the cycles before you send them home. So that's a bit of a hint as to what you're looking for on the additional question, or the last question, I think, of the assignment. Okay, so that's basically our proof. Because now I'll just sort of run through this. We've just shown how we can do this last line here, produce any one of these cycles. Now, if I can produce any 11, 12i cycle, then I'll scroll down. These diagrams just show that you can always bring any tile into box 15 by following one of these 2 paths. We used the one on the right a couple of times, this big circle, but if you needed to get 4 and 8 into the mix, you would just use this upside down L-shaped path to get either the 4 or the 8 tile into box 15. So that's all these pictures are doing, are showing that you can get any tile into box 15. And then these steps were, do your setup moves, etc., and you're able to produce an 11, 12i. And then this next step is telling you that once you know how to do an 11, 12i, you can do these ones for any I. So you can do an 11, 12k and 11, 12j. And if you do a 3 cycle 11, 12k and another 3 cycle 11, 12j, then what you have actually done is a double swap. you will have swapped the objects in positions 11 in J and 12 in K. And you don't need to think about the board in order to see why this is true. You just do the multiplication of the 2 3 cycles. 11 goes to 12, 12 goes to J. Okay, so 11 goes to J. J goes to 11. Oh, so 11 goes to J, J goes to 11, so that 2 cycle is closed. So you just do the multiplication and you get that it's the product of these two cycles. And then you do a little bit more work. You say, well, what if I took an 1112K, an 1112J, multiplied it to an 1112I, and then did the inverse of this stuff? Do the inverse of it. So 1112K, 1112J, then do an 1112I, and then do the inverse of that first thing, which would be essentially the 1112K and 1112J. It's okay, it's not in some sense quite the inverse, but it's sort of, maybe I shouldn't write the inverse because the 12s and the K should be mixed around, but we're doing some sort of extra product here. And the idea is that we end up getting an IJK 3 cycle. And that's the thing we wanted to know. Can we do any IJK 3 cycle? Yes, we can, and we can do it as a product of a bunch of these 11, 12 blank 3 cycles. And there we're done. See the little box at the end. We're now able to produce any 3 cycle, so we can produce any product of 3 cycles, so we can solve any even permutation, and therefore permutations are solvable if and only if they are even. Now I will say that this is a theoretical answer. In practice, you could do this to solve the puzzle, attack each permutation, each 3 cycle one at a time, but we already saw that to do 1 3 cycle, that was a lot of moves just to do the setup. Then we had to do the fundamental one, then we had to undo the setup. And that's only to do 1 3 cycle. What if the permutation was a product of 6 of these 3 cycles? Then we had to do this thing, well, the 6 of these type of 3 cycles, but each one of these 3 cycles, 11, 12, something, is used in trying to produce a single 3 cycle. So we'd have to do 5 of those kinds of 3 cycles in order to get a general 3 cycle, and then maybe we'd have to do 6 of these 3 cycles. So the idea is that this is a good theoretical result, but it's practically not the way you want to solve the puzzle. You don't want to do it 1 3 cycle at a time. So that's the next step, is what is a strategy for solving the 15 puzzle? And I'm not going to use my visualizer, my tactile one, the one that I'm using my hands on. Instead, I'm going to go to the 15 puzzle page, and I've got a 15 puzzle here, a digital one that we can use. And so now we're transitioning. We have our theoretical way that says you can solve any even permutation on the 15 puzzle with the box empty tile in box 16. And we've attacked it by showing that of those 653 billion, they're all products of 3 cycles. And we can further express them as to products of 3 cycles in the form of 1112I. And so if I know how to do an 1112I, then I can do any 3 cycle. And we established how to do an 1112I. And so theoretically, we could solve any of these permutations. Now let's see how we will do this in practice. So I will shuffle. So this spoiler alert. If you want to keep on continuing to try to struggle and learn how to solve this on your own, and you don't want any hints, have a good weekend. Reading break is next week, so we'll see you on Monday. You're certainly welcome to go free at this point. If you've been playing around with this and you'd like to know some strategies, then stick around for the next couple of minutes, a minute or two, and I'll show you some strategies that can help us in dealing with this. So the first strategy is I want to get 1, 2, 3, 4, 5 across. Sorry, 5. No, I don't want to fit 5 tiles across the top. I want to get 1, 2, 3, 4 across the top. So what I will do is I'm going to try to build what's called a train or a snake. And the way I'm going to do that is I'm going to try to get 1, 2, and 3 and 4 all snaked together. And so I'm just going to keep moving these things around. Okay, I want to get 1 and 2 together. I'm going to try to get that 3 out of the way. There, now the 3's in with the snake and the 4's in as well. So see how I got this snake pattern here? Now what I do is I just snake it into place. and maybe you can see what I'm doing. I'm just going to run around the outside of the board with it, and I'm going to snake it into place. We're getting there now. And we could speed this up by just sort of attacking some of the, I don't have to go all the way around the board. I just need to make room in the top to get them into place. And maybe I'll just do a couple of things like this. I'm just trying to create space, and bang, I got 1, 2, 3, 4 into the spot. And I do the same thing with 5, 6, 7, 8. So I've got a 5 here. I'm going to want that 6 to come across. I'm going to try to see if I can get that 6 to slide into place. Coming in behind the 5, there it is. 5, 6, and then I need the 7 to come into play as well behind it. There we got a 7, and I need the 8 behind it. That's good. Oh, there's going to be a problem here that I can't make space up here. So I'm going to temporarily get that 8 out of the way to make space. Pop that 5 up there, and then now I can slide the 8 in. So now I've got 5, 6, 7, 8 as a train, and I can slide them into place. And I've got the second row done. Now for the next row, we're running out of room at the bottom. And this is what typically is referred to as the end game in these puzzles. Once you have a lot of things in place, it's harder to get the last few pieces into place without messing up what you've done. So I've got the 9 in the spot. That's perfect. The way I'm going to do this is I'm not going to go for the complete row in 9. Now I'm going to start to attack it by these 2, and then these 2, and then the last 3 here. So I went for the first 2 rows, row 1, row 2. Now I'm going to go column 1, column 2, column 3, column 4. So I'm going to pan across these columns at the end. 9's already in the right spot. What I need here is 13. And this is really the only trick in some sense, the only move that is worth remembering, because it's the only kind of special one that helps in these kinds of situations, and it is the following. If I want to get to 13 where the 10 is, I just make a little bit of room here. So I make a little bit of room. I'm just focusing on these 6 squares. What I'll do is I will hide the 13, I'll stick the 13 right next to where I want it to go. And now what I'm going to do is I'm going to try to bring that 9 out, partner it with a 13, and slide them both in. In order to do that, I need to get some room above. So I'm going to slide the 13 back to bring the 10 out. Then I can bring the 9 down. And now I want to get the 9 and the 13 together. The problem is that 10's in between them, but I've got now space in the top. So I'll use that space to my advantage. Get that 10 out from between them. Now the 13 and the 9 are next to each other, and we can apply that same sort of train technique or that snaking technique to snake them into place. And we can do the same for the next one. So I got a 10, I'll slide the 10 across, and I need to get underneath the 10's got to be the 14. So I will bring the 14 around so it's next to where it needs to go. And then I'll use that same sort of gapping technique where I slide it out, bring the 10 down, slide that across, use that space to get 15 out from between them. Now the 14 and the 10 are next to each other. Get these out of the way to snake them into place. And then at this point, I have 3 left to solve. And there's only going to be one thing I can do, and that is 3 cycles that cycle them around. So that's the solution strategy technique to go forward if you're playing right from the start. This is, that's the way you can do it right from the start. Some of the homework assignment questions, though, are asking you to do something that's a little bit simpler than this. So I wanted to do that as in, here's how you could go about solving any configuration. For the homework assignment, it does ask for other things, and I'll just show you one of those, and then we'll call it for today. Because we're pretty much at the end here, and I don't want you to go off onto the break without having sort of maybe seen something like this. So 9, 10, this is an 11, and 12, and a 5. So that's all in the solved state. Let's just say I'm trying to get the last few pieces into place, and I got to do a 3 cycle, say something like this. So I got down to the last row, and then all of a sudden I'm like, oh, 9, 10, and 11, they're all out of place. Everything else is in place, but 9, 10, and 11 are not. 9 has to move to the left, 10 has to move to the left, 11 has to come around. So there's a 3 cycle. 9's got to go to 9's got to go to 11, 11's got to go to 10, 10's got to go to 9 in terms of boxes. So here is where our proof technique for showing that all even permutations are solvable can come into play in a practical way. I need to cycle these 3 pieces, 9, 10, and 11. And the only thing I'm going to keep in mind is that I want the 9 to go to where the 11 is. So what I can do is I can do a setup move, which brings these 3 pieces all together into a 2x2 array with the empty space. So my setup move is to just get these things out of the way, bring 9, 10, and 11 together with the empty tile with them. Now I can 3 cycle them. So I don't always have to bring to the bottom left corner with an 11, 12, and 1 extra tile. I can just take any 3 tiles and bring them all into one 2x2 array with the empty space, and then cycle them there. I wanted the 9 to go to where the 11 was, so I just cycle them around. So there we go. 9 went to where the 11 was, and then the rest of them followed suit. At that point, I've done my cycle. Now I need to undo the setup move that brought them together, and that was this move. That cycled them sort of around. And there we go. We've solved the puzzle. So it's still that sort of gamma inverse 3 cycle gamma, but in this case, it's bring them all. So bring the 3 you want to cycle together, do the 3 cycle on them, and then undo everything you used to get them together. In that case, sometimes writing those move sequences down is what we can do. So that's it for this one. You've now got all the knowledge you need to work on the final assignment for over the holidays and into early next week, which is 4 questions just playing around with this puzzle. So I'll stop the recording here.